Welcome. It is Monday, August 31st, beginning of week 6 in our distance learning endeavor, and I'm coming to you high above the Earth in the International Space Station. Right below us is the, looks like the southern coast of Europe. There's the Mediterranean down there, beautiful blue Mediterranean. And we're going to be starting a new section today on, or a new unit on functions, but now focusing on using functions to model. Okay, you'll notice there's probably a little delay in my video and voice. That's because of the distance I am from the Earth for my transponder, but that's just how it is up here in space. So let's take a look at what we got here. All right, this continues our study of functions. All right, we're going to be looking though at using two particular types of functions, linear functions, and the second one being quadratic, to model things. Okay, modeling is probably one of the most important applications of mathematics because it allows us to make predictions or run tests on things without actually having to do a live experiment. We can mathematically model what will happen. Great example of that, and this was probably a little bit before your time, but we used to test nuclear weapons. We'd actually blow them up, okay? And as a matter of fact, my father was in a nuclear test when he was in the Army, and they would blow up this was out in Utah, they'd detonate an atomic weapon, and then they would march the soldiers through ground zero, and they didn't quite have an understanding of how dangerous radiation was, and unfortunately a lot of those soldiers eventually came down with different ailments related to radiation exposure. And then after that we started, and the other bad part of that was the radiation would float whichever way the wind was blowing. So there were different towns in Utah and in Nevada that were exposed to radiation because of those atmospheric tests. So then we started doing it out in the ocean, and there's some islands out in the South Pacific that are still inhabitable because of the level of radiation. Then we did it underground, and eventually we got to a point where we could model it with mathematics and very strong supercomputers. And now, being able to do that, you're not exposing people to the harmful effects of radiation. You can do it virtually, so to speak. All right. So let's take a look at today we're going to look at a gradient. Now, gradients, guys, of a linear function. Linear is just a line. A gradient is the slope. So in the world of IB and in other parts of the world, instead of using the word slope, the word gradient is used. Okay? They mean the exact same thing. All right, so gradient, aka slope, same thing. Okay? It's a measure on how steep a line is. It compares the change in the vertical over the change in the horizontal. We call that rise over run. All right, so if we wanted to find the slope of a line, when you first learned how to do this, you pick 2 points on the line, and you can count what's the vertical change compared to the horizontal change. Now, this is okay to count as long as the scales are the same. So later on we'll do some examples when the scale is not the same, and you got to be careful when you count. But here, what I mean by the scales is the x distance here is the same as the y distance. Okay, these are square boxes. All right, so we pick 2 points, and then we want to count how to get from one point to the other, and you have to travel along a line. So in this case I'd have to go 3 units up, and then the change in the horizontal would be 2 units to the right, and we express that as 3/2. Okay, it describes the rate of change. In other words, it tells you how quickly the dependent variable changes. Now the dependent variable, guys, is your y coordinate. So this is your dependent. Which is your y. And this is your independent, which is your x. So what it's telling you is, as x changes, how does the vertical change? Now we have a line that falls as we go from left to right. And we want to determine what is its gradient. So we find 2 points that are right at an intersection on our grid. And then how do you get from one to the other? And it doesn't matter which point you pick. You could have started with the point on the top and worked your way to the point on the bottom. Doesn't matter. So in this case, I have to go 2 up, and then I have to go to the left 5 units. So my gradient is 2 up, 5 left. Notice that I put the negative right in the middle. Okay, it doesn't matter. I could have, this would be the same if the negative was on the top. What that would look like, it would be, that would be as if you started over on the top one and you went 2 down. That would be -2, and then you'd go right 5. It's the exact same thing. It's just starting at the other point. So it wouldn't matter. All right, now we've got a horizontal line. So it doesn't rise and it doesn't fall. It has 0 slope. So as we pick our 2 points, find the vertical distance between the 2 points. Well, there is none because they're even with each other. So that's going to be 0. The horizontal distance is 5, and therefore the gradient is 0 in the vertical, 5 in the horizontal. 5 got a little away there, and that's going to end up being 0. So a horizontal line has a slope of 0. All right, next up we got a vertical line, and we want to find its slope. So if we follow our same process here, pick 2 points. Okay, find the vertical distance between them. In this case, that's 3. Find the horizontal distance, that's 0. Now when we write our gradient as rise over run, we have a 0 in the denominator, which we learned is a no-no. Okay, bad things happen when you divide by 0. So that is undefined. The gradient of any vertical line is undefined. So if we wanted to draw a gradient of a certain size, okay, this comes into play if you were building a roof. Okay, building code has that the roof has to have a particular slope to it. Building roads, building a ramp, a wheelchair access ramp, there's certain building codes that you have to follow. So you need to know how do you take that and represent it in real life. Well, it's telling you what the vertical change is to the horizontal change. So this could be 1 feet, to 3 feet. This could be 1 inch to 3 inches, 1 meter to 3 meters. It wouldn't matter. Okay, so you just pick a point, any point, doesn't matter. Okay, then you measure off your vertical, which in this case is 1 up. And now the 3's positive, so I go 3 to my right and plot that point, connect the dots, and there's my line. Now when you have the slope of something, you can also express it as a grade. And a grade is the slope as a percentage. So I can take this and I can convert it into what is known as a grade. Grade is the same as the slope as a percentage. So you see these grade yellow warning signs when you're like up driving around Flagstaff, and what this 8% is here, that's telling you what the slope is as a percentage. So that is what's known as the grade. That is the slope of the mountain or the slope of the road as a percentage. So to turn something into a grade, all you do is you just divide out your slope. So this is going to be 0.33 repeating, and then you multiply that by 100. So that would have a grade of 33%. The gradient formula is the same as the slope formula. It's the same thing. Gradient and slope are the same thing. So to calculate the gradient of any line, you need 2 points. That's the minimum ingredients. You need to know the coordinates of the 2 points. So their x coordinate and their y coordinate. So the coordinates of 1 we refer to as x sub 1, y sub 1. That just means the x coordinate of the first point and the y coordinate of the first point. This would be the x coordinate of the second point and the y coordinate of the second point. And then to get our slope or our gradient, we want to find the difference, the change in the vertical or the rise. We're subtracting those two. And we want to divide that by the change in the horizontal, which is the distance between x1 and x2. So we do that subtraction, and we reduce that to lowest terms, and that is our slope. Now, as we move ahead and get into more sophisticated mathematics in this course, particularly calculus and the derivative, you're going to see this notation, which is a triangle and then a y and a triangle and an x. And that's exactly the same thing as subtracting the y's and subtracting the x's. The way that we read that, the triangle is the Greek letter delta, and that just means change. So delta y means the change in the y coordinates, and delta x simply means the change in the x coordinates. So we've done these all the time, so we're going to go through them pretty quick. Find the gradient between 2 points, subtract your y coordinates, subtract your x's. The order doesn't matter as long as you're consistent. So it doesn't matter which one you'd call x1, y1. You could have called the top one that and the bottom x2, y2. It doesn't matter as long as you're consistent in the order in which you subtract it. Now, what's of particular interest isn't so much how to calculate it, because you've done that for years. That should be hopefully fairly straightforward. But what does this thing mean? Now, we don't have any units on this right now in terms of the x's and the y's. But in just its purest form, a gradient of 3 would mean the vertical increases by 3 as the horizontal increases by 1. So for every 1 unit in the horizontal direction, the vertical direction is going to increase by 3 units. Now, if we wanted that as a grade, that means we would take the slope, which is 3 over 1, which is 3, multiply that by 100. This would be a grade of 300%. All right, find the gradient of a line segment joining the points 4, 0 and 115. Now this line falls, so we know that this is going to have a negative slope. Anytime you're checking slope, you're always working from left to right. So this has a grade or a gradient of, or slope of, -5. That would mean now for the vertical changes 5 downward, it decreases 5 for every 1 unit to the right, or 1 unit in the horizontal direction. All right, find the gradient of a line joining 0, 0 and 14, 42, and here's your drawing. Now, if you're just counting on this, you got to be careful, because the squares have different scales. So what I mean by that is, if you look at the difference between the vertical changes, it's 14. Whereas the change in the horizontal is 3.5. They're not the same. So if you calculated it by just counting, so for example, if I picked 2 points and I counted, whoops, then I would get an incorrect answer. So for example, these 2 points are pretty close to being in an intersection. And if I said, well, I got to go up 1, 2, 3, and over 1, 2, 3, 4, and I said, oh, the slope is 3 over 4, it's not. Okay, it's actually 3 up would be 3 times 14, and 4 to the right would be 4 times 3.5. And then that would give me my correct slope. So you can see my slope is actually 3, once I take in consideration that the scales are different. Now if I did it using the numbers up here, then I don't have to worry about that. The point I wanted to make is, if you're counting, you have to be careful. You need to take in consideration if the scales are different on the x and the y axis. So again here, if we counted, we'd get an incorrect slope or gradient if we didn't take in consideration the scale. So in this case, our changes in our y coordinates is 4, and at the same time our change in our x coordinates is only 2. So the scales are different. So again, counting is okay. I can say I'm going to go 2 down and 2 to the right. So if I was doing my slope by just counting, okay, I'd have -2 over 2, but that 2 down is really 8 down, and the 2 to the right was actually 4. So this would be a slope of -2. Now, if you did it using the formula, then you're fine. You're going to get you'd get your answer. I'm just pointing out what happens if you count and you don't take in consideration the difference in scale. All right, so here's a very basic modeling example of a linear function. And I'm going to show you how to do a scatter plot on Desmos and connect the dots. And it's very simple. So what you need to do is pause the video and open up, just go to desmos.com and open up a graph. Just a plain blank graph. Alright, so what we have here is we're given some exchange rates between American and Canadian dollars. On a certain day in 2017, 4 people exchanged US dollars to Canadian dollars. The amounts they exchanged and received are shown in the table. Okay, this data is linear, so when we do a scatter plot, we're going to get a line, and a line has a constant slope, and that slope is going to be the exchange rate. So what we'll end up with is some amount Canadian dollars per 1 US dollar. That's what we're looking to find out from this. So let's go to our Desmos graph, and we're going to type in this table here. To enter a table in Desmos, click on the plus sign in the upper left-hand corner and choose Table. And now what we're going to do is just put in our X value and our corresponding Y values. Now as you graph those, it's plotting them. So if you zoom out, you should be able to see all your 4 points. There we go. Now we're going to connect those with a line. So to do that, just put your cursor over the color here, and I'm just going to hover on it, and I should be able to select, there we go. I pressed down, I hovered on it, and now I'm just going to go to lines. And what it does is it connects the dots. So we can see that this is indeed a linear function, and the slope is going to be constant, which is good because you don't want the rate to be changing as you're exchanging your money. So that's what our graph ends up looking like. So let's go back to our slide now. So to get our gradient, we picked 2 points, and I did my gradient formula, and I got 12.5 divided by 10. Divided that out, I get 1.25, which means I get $1.25 Canadian per $1 US. So if we had a street that raised 3 meters for a horizontal distance of 28 meters, this would be its steepness. So I calculate the slope, which is simply going to be 3 over 28, which converts as a decimal to 0.107 and change. And then I take that and multiply it by 100, and it gives me a grade of 10.7%. So this slope and that grade are mean the same thing. It's just a different way of expressing it. All right, our next problem is similar to the last one, but a little bit more involved in terms of, because of what the information is that we're given. But in the Guinness Book of World Records, the world's steepest street is in Dunedin, New Zealand. It's Baldwin Street. Okay, it's a short residential street. It's 350 meters long. Right? From its base, at approximately 30 meters above sea level, it rises to a height of 100 meters above sea level. Okay, so if we were to draw it having it starting at 0, 0, it would look like this. This distance right here would be 70. So to get the rise over the run, what we need to do is figure out what the length is of this side right here, which means we've got two sides of a right triangle. We're going to use the Pythagorean theorem to find out that third side. So on our way to figure out what the gradient of this street is, we need to find the coordinates of B. Once we have the coordinates of B, we can use it with A to get the slope. So B right now, the horizontal distance from B, we don't know. Okay? We know the vertical distance, height from sea level. So this, our x-axis is actually sea level. So from sea level, B would have a y coordinate of 100, and now this length of this right triangle would be the x coordinate of B. So we've got to use our Pythagorean theorem here. X squared plus 70 squared equals the hypotenuse 350 squared, and then we solve that. So we did the Pythagorean theorem, and I got the length of this leg to be 342.93 meters. So my coordinates of B are 342, 100, and my coordinates of A are 0, 30. Now I put that into my slope formula, and I get 70 over 342, which simplifies to 0.204. Now that as a grade is a 20.4% grade. That's the steepness of that street. Now you probably really don't have any appreciation about if that's, well, it's 20 degrees steep or not very steep. Well, here's the actual street, and you can decide for yourself. Folks, that takes care of our quick review of gradients. Your assignment from this is Math Excel 14, 3.1a, gradient of a linear function. And this is Mr. Krolak, high above you in the ISS. That's the International Space Station. Signing off. See you next time.